everybody, but I'll introduce myself real quick. My name is Brent Ursenbach. I'm energy and mechanical code instructor is basically what I do now. My background, as many of you know, is HVAC. I spent 33 years in that. And I spent 13 years as an inspector plans examiner. And I retired from Salt Lake County in 2018, so almost 4 years ago. But I've still been doing this. I wanted to mention, and I think most of you know this also, through a contract with the State Office of Energy Development, I'm a resource for energy code. So if you have a question or something like that, you're welcome to email me, text me. You can try calling me, but it's best to text me first to see if I'm available. Like if someone wants to talk to me today, they're not going to be able to talk to me today. And I'm here to assist you. We do a lot of classes. And if you have something in your jurisdiction that you need some help on, feel free to reach out to me. And I'm going to continue to do that for at least a couple more years, and maybe I'll do it for more after that. It's just when I decide I've had enough. But anyway, our sponsors are supporting us at Rocky Mountain Power and Dominion Energy, which means you don't have to, I'm getting paid to do this stuff. So you don't have to apologize and call it and say, hey, I hate bugging you, because I'm being paid to be a resource for you guys. So feel free to reach out to me. Obviously, everybody knows what the class is about. And don't be shy. How many are right at the starting point of manual JD and S? Very little experience with it. Okay, that's what I figured. Then some of you have probably been working with it for a little bit longer, and some of you, it's just like any other part of the code, especially energy code. We find people, some jurisdictions are really gung-ho and they've grabbed onto it and they realize the importance and it's part of their process, and others are just starting to become more familiar with the energy code. It's not a required certification, but it's an adopted code, and so we have a responsibility to enforce it. And coming from my background, I'm an energy code specialist, I guess, because I learned in 1973 and 1974 how to do a manual J load calculation by hand. We didn't have computers. It was a big
little
paper
calculator.
Yeah, duck calculators, and you took your manual J.
Rule duck calculator.
I got a manual J here someplace. And it wasn't this big. There's two versions of manual J that are printed right now. But you took your manual J and you looked up 2x4 walls, 16 inches on center with an R11 bat in it. And you pulled a number out of the table. You put it on a spreadsheet, you added the areas and everything, and you hand calculated this whole spreadsheet, and you added it all up. And you found out what the house needed. That's exactly what we do with manual J. And manual D is how we do the duct system, manual S is how we select the equipment. And so I could do a week on manual J and we still would have covered everything we want to cover. So what I'm going to cover today is the basics, and I am going to change a little bit. If you've been in my class before, I've given you an example. We've tried to do this at the end after we go through all the materials, so I'm inserting pieces of this in the presentation as we go through so that you can kind of see what this is. Anyway, this will make more sense as we get into it. So what we're going to talk about a little bit today is our Utah code and our adopted code. I think most of you are familiar. Utah, our energy code is probably one of the most amended parts of the code. Our energy code is very heavily amended. And some of those amendments are really poor amendments. What they do is they don't protect the homeowner from condensation and air quality issues and stuff like that. But I'm going to talk just briefly about that. I'm going to talk about a DOE study that we're in the middle of working on right now, where DOE had some grants and some funding for homes in Utah and Arizona to be inspected, at various stages of construction for compliance with the energy code and what we learned there. And then we're going to talk about the ACCA standards that are in the code. So I'm going to ask a question. The code does tell you you're supposed to design your HVAC system based on ACCA Manual J. Grab some handouts right over here. So if the code references Manual J, D, and S, does that mean this book is code?
It's a reference. So
it's a reference standard. So if it says you do it for this book,
it is. It's an appendage to the code.
Yeah. And if you go to the last chapter in every I code, what do you have? All the reference standards. It's like the IBC references the concrete standard. What is it, 318? Yeah, that's code. This is really code.
And it's critical what edition it is, because it may not be in tune with what code edition is.
Yeah, exactly. And it needs to be the right edition. So these are the standards that are listed in the code, and by reference, they are part of the code. It's not, well, if I want to or whatever. And then we're going to spend some time trying to understand that code right, this thing right here. So I've given you a handout for the slides, and I know it's small, but I did it so you can make a note by a slide or something like that. And I printed it so it goes this way. If you go this way, it's going to be upside down. If you flip it up over the top, it'll be right side up. But if you don't even want to pay attention to this and just pay this, and if you want full page slides, just send me an email and I'll send you the PDF of my presentation. So our DOE study, and we're right in the middle of this right now. The goals of the study were to collect field data to generate a baseline compliance rate across our two states. So they wanted to see, okay, is Utah and Arizona, are they 50% compliant with the code? Where are they strong? Where are they weak? And guess what? We had some big surprises with the study. And the whole purpose was to develop targeted education. So as I participated in this, I'm at the point now, we've got the results of the study. They want me to incorporate it into my presentations so that we improve where we need to improve. And so this is where they sampled homes that really, they sampled 63 homes, 7 in Harriman, 3 in Saratoga, and down on through North Ogden to St. George. Well, there's Hurricane. Anyway, there's Ivans. So they surveyed homes all across the county, the state, and then they generated, this was generated on permits, and there was no identifiable information. So if Hiram, for instance, is doing nothing, no one knows it was Hiram. That makes sense? And here's what they found out. If we adopted the current code and enforced it annually across the state, there would be a $620,000 savings just by improving the wall insulation. Why is our wall insulation so low? Because we have a state amendment that allows you to do the Utah res check, right? I get calls all the time. How can they build a house? How can they build a house and put R11 or R13 in the wall and pass a res check? And you can, because we have an amendment that lets you trade off walls for a better furnace. And so we build a wall that's 25, 30-year-old insulation standards, and we can get it to comply with the code because we have an amendment. Now, those that support the amendment say, well, yeah, but we can gain that extra efficiency with our furnace. Well, great. But we have one chance to build a wall right, and we've lost the chance to build it better.
How long does the furnace last? How long does that last?
Yeah, how long does the furnace last? How long does the house last? You know, this is a minimum code. So that's the big thing. We should be building an R20 wall, or R21 wall, or somewhere in there for everything. And you can build an R11 wall and get it to pass by doing trade-offs. Duct leakage. $250 million right here where we are right now. If in St. George they took the furnaces and the duct systems out of the attic, they'd basically reduce their energy expense in the summer between 25 and 50%. So up to half of their energy expense is being thrown away because everything's in the attic. Please.
So, at jurisdiction I work for, we require them to do the duct blast test.
Right.
And I spring that on new contractors when they come in and they're like, what the hell is that? So, and that's just when they have the attic furnaces,
right,
or the 25% more of their ducting in the attic or whatever.
Okay.
So I don't know how many jurisdictions are requiring that type of thing, because everybody acts like it's a surprise, and
We do.
Yeah, the comment, and by the way, I'm recording this because the state wants it recorded as part of my contract with them. So I'm going to repeat a little bit of what you said so they can hear it. Basically, what you're saying is you require the duct blaster test that's required by the code.
And blower door testing.
And the blower door testing. And I don't want to spend too much time on this, but that's one of my main purposes through my contract is to, rather than Doppel beating everybody over the head and say you have an inspector's license, you have to enforce the code. We want to train people so jurisdictions say, hey, I'm supposed to be requiring this just like I require a footing inspection or whatever. And we are improving, but we've got a ways to go, please.
Well, what I've seen, I had over the years, unfortunately, I've worked in jurisdictions that are true believers in it, and others that go, huh? And it didn't matter what size the jurisdiction was either.
That's right.
I can tell you some jurisdictions of 10 million people do not, and trust me, the state of California is not on the cutting edge either.
No.
The reality I see the biggest problem is, one, it's a minimum standard, but everybody goes to performance to get the trade-offs as much as possible, cut the cost as much, but they don't read what the performance requirements are, including the commissioning requirements. And since most jurisdictions, literally, I have 90% of the jurisdictions I've dealt with, do not require the test results, the commissioning, the report at the end of the project before the project. Most jurisdictions don't even require the sticker to be put on there to tell you what kind of insulation is in the wall.
Yeah.
And the commissioning is the problem in my world. My estimation is you're asking commissioning to be done, but nobody is requiring that commissioning follow-up and making sure it's getting done. So they get paper to the cities showing their compliance certificate, and life is good. Whatever happens in the field happens in the field, and the house gets CO'd, and there's no building official told to CO because they didn't put insulation in the walls.
Yeah, it's a problem, and, you know, what we're talking about today is one of those problems that isn't being enforced, right? And it's a hard one to enforce, and it's one we gotta be a little careful enforcing. But anyway, so this is what the study showed. I'm gonna move on because I got a lot to cover. Walls, duct leakage, ceiling insulation a little bit, envelope air leakage. That number is lower than I expected. Window U factor, you know what? Even if you're not enforcing the code, the windows, you buy a low E window today, and guess what? It's a good window, you know? And it's just kind of an automatic thing. And lighting isn't a big deal because LED lights are so cheap now compared to what they were. So anyway, the big takeaways were, and all this study looked at, it did not look at, it focused on the envelope, and it didn't look at the HVAC systems really. But off-the-shelf items like windows and lighting are highly compliant. This is the big one. Air leakage is really low. Now, many of you know that, and some of you don't, but our state amendment says that you either do this comprehensive inspection checklist, air barrier and insulation checklist, or you do a blower door test. Now, some jurisdictions say, let people say, well, we're going to do the checklist, and then they don't check the list. And some blower door tests, but what we're finding in this study, that most of the homes are tight. So if you're building a home that's tight and you don't blower door test, what gets missed? Mechanical ventilation. What's mechanical ventilation? It's some form of continuous fresh air being brought into the house. So we're building a lot of tight houses and we're not ventilating them right. So what does that mean? We have poor air quality, we have moisture, and when our relative humidity goes up, our dew point, we hit our dew point, and so we're condensing all over in our walls, and we have mold and mildew and all this, and we have just a multitude of problems, and people are going to be finding in 10 or 15 years that all the, not even that long, all the cladding's fallen off the side of their house because their OSB is rotted away. And it's because they built a tight house and they didn't ventilate it. And they didn't do the weather barriers right in some cases, but a lot of them, the moisture is coming from inside. And it's because we aren't enforcing the whole code as an integrated set of codes. We can do really good on part of the code, but if we don't get this one right, we have a home that has some serious defects. Ceiling attic insulation is generally close, and in fact, some of these numbers, well, I'm not going to back up, some of those numbers are a little skewed because the study was based on the prescriptive table, and it did not, so it said R20 in a wall, or R38 or R49 in an attic, and if it was less, it did not have it couldn't recognize that they might have traded it off with what that high efficiency furnace, which means you build a bad envelope and you put it in a high efficiency furnace.
If you look at manually, these make sure they match.
That's exactly this one, Jason, right? So my number one thing that drives me crazy when I review a plan, and I don't review too many of them anymore, but this is across, I review plans in California, I review them from lots of states across the country, whether it's Utah or someplace else, is just what Jason was just saying. We have a set of construction documents, whether it's a residential or commercial building. With a commercial building, we have more documents, but nothing matches. The R values and the U factors are inconsistent across all the documents. That's nuts. How are we going to get a building built right if the res check says it's R20 in the wall, but when they build it, it's R13? You know, it's, so anyway, that's my.
I think that the biggest problem that I have come across is that you have different contractors and architects not working and communicating together. And nobody knows what the left hand is doing with the right.
Yeah.
And as inspectors, we have to be, and plan reviewers, we have to be the ones to enforce that. And I'm finding that there are so many that don't.
Yeah.
They
Yeah.
just pushed it through because there's such a work overload right
Yeah,
now.
Yeah, and contractors don't want to pick all of their subs at the first, you know what I mean? And
Yeah.
they want to change, but yeah, the big thing is the design team needs to be a team. And they need to be communicating. And it doesn't help that the legislature says, well, you have so many days to get the plan review out. And so maybe you just need a sheet that says, you know, this is what we expect, consistency and stuff like that. But yeah, rarely do I see a res check that matches the plans or the load calculations. And isn't it important that the HVAC is designed based on how the house is going to be built rather than not how it's going to be built? So, some of you have seen this before. I've got to get it out. Here we go. So that we don't have to sit through this class, how about I just go stand at the curb and I figure out which hole the house fits in.
That's worked for 50 years.
It's been working for 50 years, hasn't it?
That's what they all say.
You know what? You know, this is obviously a joke, but when someone says, I've been doing this for 30 years or 40 years, I know what size of furnace, so I do a ton per 600 square feet or 500 square feet, and it works. That's exactly what this is doing, isn't it? If the house fits in this, it's a 4 or 5 ton. If it's this one, it's a 2.5 to 3.5, and if this one's, it's 1 to 2 ton air conditioner. That's all you need to do. What's the fallacy with that? Do we know which way the house faces? Anybody have a house with west glass? When the sun gets on it in the summertime, does that room get hot?
Yeah.
Really hot, right? If your house would turn 90 degrees and that glass was facing north, there'd be no sun on it. That changes the air conditioning load completely. Lots of glass or just a little bit of glass? Wall insulation, is it R11 or is it R21? You know, all these things make a difference. And so the only way we can properly design an HVAC system that gives comfort is to do a load calculation. Now, when I started working in HVAC back in 1972, we didn't put air conditioning in hardly anything when it was first built. Even the luxury homes, they would say, oh, we'll wait and see what summer's like. And then we put an air conditioner.
Might rough it in.
Yeah, and you rough it in or something like that. Matt grew up in the same neighborhood that my family was. I have boys, well, my boys are older than you, aren't they?
Mark's the same.
But anyway, we all, Josh, when I bought that house in 74 or 75, I think your parents bought the next year or something like that. None of them had air conditioning. None. Do you build a house today without air conditioning? Do you buy a car without air conditioning? No. The public demands more comfort. And if they're going to want comfort, then you're going to have to do a load calculation. They're going to have to, otherwise they're going to be complaining to your jurisdiction. They're going to be complaining to their builder. They're going to be complaining because they want an even, comfortable house.
Do they, when they're doing the load calculations, do they take it into consideration the directional of what? the house is?
Absolutely.
Yeah.
Is it orientation?
Yeah, that's the word, the
Yep.
orientation.
Yep. And we'll show you on this how you check it. In fact, that's one of the things I look at when I look at a load, is you go back to the worksheets. That's these sheets that are partway back.
You're right, Jay.
And there's a column that says OR, orientation, and it has an N or an E or and so you can input a house, and then you can just change the orientation, and the house rotates and it gives you a new load. That's the beauty of
Because I was gonna say,
computers.
a guy that's been doing it 30, 40 years probably is better to show up on the job if he's got that kind of experience, which way it's oriented, and then do it from there.
Yeah, but he needs to,
But you know what I'm saying?
I do.
Like, if you had a guy that's done this all of his life, and he shows up on the house, he's like, this bad boy is gonna have a ton of southern exposure, this is what we're gonna do.
But he needs to.
But if, and that was my question,
Yeah.
but if they're already figured in, then it's.
Yeah. See this page back here? What do you see right up here? There's a little compass. All you have to do is switch it, and it turns the whole house. Now, back when I started doing it by hand, if you rotated the house 90 degrees, guess what you did? You filled up a whole new sheet with all new numbers and added them all up again. When Wrightsoft first came out in the 80s, right after I bought my first computer, it was great because I could put in a house and I could change the windows and see what it did, or, so. Anyway, you've heard me say manual J, manual D, manual S. We're going to talk about those. Equipment sizing. Load calculations determine the proper size of the equipment. The goal is big enough to be comfortable, but no bigger. So why does it matter why can't we be oversized? It's short cycles, it's inefficient, and it's not comfortable. If all you had in your car, and Jason, you've heard me say this before, and others have heard me say this before, it's all you had in your car was a switch for your heat, a switch for your cooling. And when you get in your car and it's cold, you turn it on, and when it gets hot, you turn it off. And when it gets cold, you turn it on, and then you turn it off. You won't be very comfortable. That's what our house does, unless we have, more current, updated, multi-stage equipment and stuff like that. It turns on and off. When we're driving our car, now a lot of them have automatic thermostats in them and stuff like that. But don't we want our car, when we're driving like a long distance, don't we turn down the fan and turn down the heat until we get to a sweet spot that we don't have to touch it? What's happening at that spot? We're adding heat in the wintertime at the exact same rate we're losing heat. That's the ideal HVAC system. We add the heat at the same rate we're losing it, so we're gently adding just the right amount of heat to maintain comfort. And then in the summertime, we do the same thing. We just remove heat at the rate that we're gaining heat from outside. And that's why we want to size that so it's not on and off, so that we have uneven, imbalanced heat. Manual S is just how we select the equipment after we've gone through the whole process. We'll talk a little bit about that. So our load calculation, you have this sheet in front of you. You have 22 pages. We'll break that down a little bit. I've already said it's in the code. And what does manual J really look at? It looks at the thermal envelope. The thermal envelope is any construction component that separates conditioned from unconditioned space. So that could be a cantilever, right? You have a little cantilever. We're unconditioned on one side, we're conditioned on the other side. It could be a garage. So you have a garage on one side, you have a house on the other side. That's part of the thermal envelope. Anything that separates conditioned from unconditioned space. And that's what we look at when we do a load calculation. All those components of that thermal envelope. We look at design conditions. What do I mean by design conditions? And this is one, and I'm not saying this is a bad thing, but this is one that a lot of jurisdictions spend all their time focusing on the temperature we design at, when maybe some of their energy should be someplace else. And we're going to talk more about that. Fenestration, windows, doors, and skylights, walls above and below grade, ceilings, floors. Infiltration. Why does my truck or my car seem to cool down so fast? If I were to do that switch thing and just shut it off, wouldn't I immediately feel cold? Because it's leaking, right? It's leaking around the doors, it's leaking air. Cold air in. into the, and we add to the air leakage by doing what? By driving down the road at 80 miles an hour. That increases air leakage. What increases air leakage on our house? Wind. Internal gains. We look at internal gains in the summertime. What's an internal gain? That's cooking, that's breathing, that's living in the house. We generate heat. I'm staying next door, and I walked into my room last night, and it was 76 degrees in the room. And the system was off. I was at 76 degrees.
You're probably above the laundry room.
Well, I'm third floor, so I'm above another unit that heat comes up from. And it has the full refrigerator, and it has, and what does the refrigerator add? Heat. And how much outside wall, how much thermal envelope do I have in a hotel room? I have one wall, right? One little wall. And guess what? The sun was shining through it for just a few minutes. But internal gains are becoming a problem, actually. Apartments, all these big apartment buildings that have one little wall. And the people are turning on their air conditioner because it gets 80 degrees in there because they're heated below, they're heating on the sides and everything else. And you cook and clothes and wash your clothes and wash your dishes and all that stuff, and you add more heat than you lose. And so it gets hot in the wintertime. D, we'll look at that as we get a little further. So what's a load calculation? A load calculation is an analysis of the thermal envelope, as I said. If this room was a standalone room, a single building that was this room, every wall would be thermal envelope. This was outside above. All we would do for a load calculation is we would analyze every square foot of the entire room or the entire building to see how much heat is going to be lost in the wintertime and how much heat is going to be gained in the summertime. We'll look at the conduction through the envelope, and then we'll look at the air leakage. And then we'll look at the solar gain. And we'll look at every component and how much heat transfer we have going through it. So what is heat? Well, heat's energy. What is a heat loss? Well, heat loss we do in the winter on how much heat we lose. What's a heat gain? We do it in the summer. How much heat are we going to gain? The maximum load that will be placed on the piece of equipment. Now we're faced with a challenge in a home because we want to design it so that it virtually runs almost all the time on the very coldest conditions. But 99% of the time, we're at a different condition. And so it's oversized all the rest of the time. Heat must be added to replace what's lost, and it must be removed in the summertime. So what does an air conditioner do? It doesn't add cold to your house. It removes heat from your house and takes it out. Load calculations. Pros and cons that I hear. You don't need to do it. Been doing it. We talked about that. I got a good rule of thumb, don't I? Right here. Bigger is better. Waste of time, dumb code. Pros: comfort, even temperature, air filtration, humidity control, adequate ventilation. I don't have anybody in here from Moab, do I? Bill and Cole had me, I went down there 3 times last year and taught in Moab, and we did energy code, the whole energy code. And I stayed at I can't remember the name of the place, but it's these little small cabins, just you're coming into town, really nice. And they had those little Mitsubishi multi-zone little units, little air handler hanging on the wall in every room that are variable speed, inverter technology. And those little units run virtually all the time at exactly what I talked about. Adding heat or removing heat at the exact rate you need it. So you hear this little whisper all the time, but the temperature doesn't change. You don't have this on and off. Incredibly comfortable. And the whole thing is we want comfort, and then I should add on there, building durability. Quality. Efficiency, increased equipment life. I bought a GMC Denali from my brother a number of years ago. He went to trade it in, and they wouldn't give him hardly anything for it because it had 100,000 miles on it. Well, the 100,000 miles were driving from his home in San Jose to his mountain home up by Lake Tahoe. So all it had done is drive freeway miles. Was it worn out? No. You buy a car like that, rather than stop and start, and you get 2, 3, 4 times the longevity out of it because you're just steady state, motor's all lubricated, all efficient, you're not accelerating and stopping, and, I drove it 100,000 miles. I was still, did brakes at 150,000 miles because it didn't start and stop. Okay, I just praised doing a load calculation. Does a load calculation ensure perfect comfort? No, because there's a bunch of other stuff and the number one on the list is the duct is not installed for the duct design. And that is the biggest thing that I see out there in the field. I have some associates and friends that do in the HVAC industry and in the testing industry, and more than 90% of the time when they put airflow testing equipment on residential HVAC systems, it's like 94, 95% of the time it does not have the airflow that it was designed for. And it's because of the duct system. If you take a garden hose, I don't know if you've noticed this, I have a couple of those hose reels, that wind up your hose. And you wind up 100 foot of hose on it, and you pull off 5 feet of hose and turn on the water, and the pressure is not that good, but you run it out straight, and the pressure goes way up, doesn't it? Because they don't have turn after turn after turn that the water's trying to go through. And if I roll that out and then I kink it 4 or 5 times, how much water comes out the end? Almost nothing. What happens if your duct system, you do this, and then you do this, and then you do this, and then you do this? You're kinking it every time you put a square 90 in it with no means to direct the air around it. And 95% of the systems that you see every day have kinks all over in them. And generally the load is designed without the kinks. Sometimes the house isn't built per plans. There are incorrect information was provided. It doesn't match. It's not the consistent information. Multiple levels and wings. Back in the 80s, late 80s and early 90s, I had a contractor that I did work for that built, and it was a big deal back then, was these multi-levels, 4 or 5 levels, those splits, and they split side by side, to the sides. And those are hard to heat and cool because you're trying to comfort condition 5 levels. And we had the most success. Now, no one wanted to pay for dampers and zoning and all that stuff. We put in a 2-stage furnace, so in the winter time, when it was really cold, it ran on the first stage, half the capacity, almost all the time. And if it needed a little extra heat, then it would jump to the higher stage. That way we had a constant flow of circulation of air. But if you have an oversized furnace, it turns on, shuts off, what happens? The warm air rises, the cool air drops, and you have 10 degrees difference between the basement and the top level.
Do those 2-stage furnaces automatically switch during the day? It's automatic.
And then we have them now that modulate, that just, but yeah, it depends on what thermostat you put on. If you put on the right thermostat, yeah, it's completely automatic. If you don't, you put on a standard thermostat, They'll run 10 minutes on low and then they'll jump to high if it doesn't satisfy them. But it does help because you're not always so grossly oversized. You build a house and you have a wing going off here and a wing going off here, and you have a room over a garage and all that stuff. I don't care how great your design is. When the sun hits it from one direction or another, it's going to change the whole dynamic and you're not going to be as comfortable. So load calculation is the first step. It's not going to give 100% perfect comfort. I had a guy call me and he said, I did a load and I was really careful and the load was as good as it can get, but we have a little mother-in-law apartment off on the other side of the garage that the homeowner's mother was living in, and she's always cold. Well, number one, the thermostat was on the other end of the house. There was a hallway literally that went around the back of the garage over to her little apartment. She wanted it warmer. It saw the sun different. There's a whole bunch of things. Sometimes you have to put in zoning. Sometimes you have to put in mobile systems if you want the comfort. So just by requiring a load calculation doesn't mean that the homeowner isn't going to have a complaint. Improper operation, refrigerant and mechanical issues. So often it's easy to blame the inspector for making us do a load calculation when in fact there's something wrong, the charge is wrong, the line set's keyed, there's something wrong with the system. And each occupant wants a different condition. How many of you that live in a house with more than one person agree with the temperature that everybody else in the house wants?
I agree with her because she told me what to set it at.
Yeah.
I can pick up my phone right now and I can guarantee, and look it up, and I can look at my thermostat and I can guarantee it's on 75 or 76 right now. And if I don't turn it down to 70 because I like peace in the household, but I prefer it 70. And guess what? We are all different. I go to see my dad, he's 98 years old. And I'm half tempted to put on workout shorts and a t-shirt because it's 83 degrees in there. If he were to build a house for himself, would the inspector be okay and say, no, you can't design for 83 degrees? No. I think we need, the recommendation is we design for 72 for heating and 75 for cooling. But I think we need to be reasonable and we need to recognize that some people might have health conditions or they just might be a little bit different temperature. So build a real good envelope and let them put it where they want to is my. Sometimes we just have to zone. So let's talk real quick about the thermodynamics, the building science, and don't cringe when I say building science, but this is all science, it really is. We have what we call thermal conduction. And that is we put heat at one end and it goes to the other end. And how quick the heat goes or how much heat moves is based on what?
The conductor.
The conductor. Is it a conductor or is it an insulator? I don't know. You have a comment, Jason?
Well, just going back to what you said about let them decide. You know, I always put on my comments, please explain why you've done this. But especially in Summit County, you know, I get contractors come back and they say, because the ceiling in that room is 23 feet tall.
Yeah. Yeah, if someone submits something that's unusual, ask them to justify it.
Yeah, I don't know.
With a reasonable
I
justification.
ask them why.
Yeah, please justify. You know, it's really amazing how by saying please justify, you know, I use the word please in my plan review comments all the time.
Yeah, even on your occupant load, if they're gonna have a daycare or a preschool in the basement, half the day there's gonna be 20 people in the house versus, you know, one or two person or
Exactly.
So when your occupant load shows up at 25, you're like, what are you doing in there? I mean, just, Jason said, you can ask that simple question, send an email, make a phone call. Oh, this is what we're doing. Okay, perfect.
Yeah, occupant load, let me comment on that one real quick first. Occupant loads are things that I see all the time, but sometimes I've asked for justify it, and they'll say, well, we have everybody over for Thanksgiving. And they're adding a lot of people to the cooling load.
That's an
Well,
outlier.
duh.
It's not.
It's not when we need the cooling, so, you know, you can't add 30 people to a home for an event that happens for a few hours a day, one day of the year. You know, that's not, I don't accept that as a justification. And if I have that many people in my house and we're cooking and everything, guess what I'm gonna do on the 25th or 6th or 7th or whatever it is of November? I'm gonna open a window, right?
Well, like Summit, I was heading to Colorado, and they're transient residents. They got their 10,000 square foot house, if they're there 2 weeks a year. And they all have radiant floor heat and boilers.
Yep.
And sidearms. And the problem is it takes 4 to 5 hours to heat that house up with radiant floor heat. The other problem is they have a lot of glass because they're paid millions of dollars to see the view. And as soon as the sun goes down,
It gets cold.
it gets cold there, and that heat can't, the radiant floor heat can't recover that quickly. So they end up putting baseboard heating along that glazing to make up the difference. So the point is it depends on where you're at and the people that you're dealing with. I accepted some of them things because of who's going to be there. I didn't want them to heat that house at 70 degrees year round, which some of them do, for that 2 weeks.
Yeah.
And so I prefer them to have an overloaded system.
So they
They
can
can
recover.
break on that day that they're gonna come for their 2 weeks.
Yeah, yeah, we do have those, we have the transient things, you know, and you build a cabin and you drain it out and it gets cold. My father-in-law and I built a couple of cabins years and years ago. Boy, you go up in the wintertime and snowmobile in and turn on the furnace and build a fire in the fireplace, and it's the next day before the frost is out of the sofa and the beds and stuff like that. And so we do have those things, so yeah, we just need to ask to justify some of those things, but we don't want to put in a single system that's so grossly oversized that it's brings you up quick and then you're uncomfortable the rest of the time and it's inefficient. So this is the conductor. I don't know if you've ever done this, but we used to go up in the mountains when I was a kid, and you want to cook some hot dogs and you forget the sticks, or you can't find a stick, so you take a coat hanger and untwist it. And you ever tried to cook a hot dog on a coat hanger? Your hand gets hot real quick because why? Because the wire is the conductor and the heat comes straight up the conductor. So when you buy a hot dog stick at the store, they have a little wood handle on it, which is an insulator of sorts. It's about R1 per inch, so it's a whole lot better than the steel, so you don't burn it. So we have the conduction. The energy is moving through it because it conducts, or it's being slowed down because it's more an insulator. That's what we're doing with our thermal envelope. Then we have what we call convection. And convection is we move energy in air or a fluid. And so we use convection with a forced air system to move heat, but we also see convection as we move heat out of our building through air leakage in the walls, right? Or the roof. And in effect, every house built, every building built has an opening, however big. If we don't build a tight envelope, it might be a 3 foot by 3 foot opening in the building because of all the little leaks that we add together. And that's convection. So we have to, in our load calculation, we have to account for the heat that leaks in or out by convection. So we have it moving through the wall by conduction, we have it moving through the wall by convection. And it's just like leaving a window open. And then we have what we call radiant heat. And that's what we feel coming off a fire. It's what that radiant floor actually radiates some heat up. But what we really notice in HVAC is the radiant heat from that west window. That's a radiant heat that's coming through our window in the summertime that we haven't to remove the heat. Now, I built a house back in '94. I've since sold it, and it faced, I don't know what direction, south, right? It faced, wherever. Yeah, it's back here. Yeah, because the front door's there. So it faced south, just slightly southwest. And I had a library office room, right off the front door, and then I had my living room. And they both had big windows going up. And guess what? In the wintertime, they got hot. I had low E glass that blocked about 70% of that radiant heat, but 30% came through. And because I had sprayed foam in the walls and all this other stuff, I wasn't losing very much heat, and I was gaining all this, and those rooms got hot. And so I had to open my window because of the radiant heat coming through in the wintertime on a sunny day. So we have heat loss and heat gain. I'm just going to load these all up. Wintertime, we have a loss through the roof, maybe 30, 40%, windows 10, 15%, walls 20, 30%. And these are just typical numbers. Infiltration and ventilation 10, 15%. Some of those are even higher than that. And then we have a little bit through a floor depending on our construction. So we have heat being lost through all those, including air leakage, infiltration. Then in summertime, we're gaining in all those places, but especially through the windows, and especially if we have a dark roof or a dark wall. You drive up I-15 in Salt Lake, and I think it's a climbing thing or something that they build off the side, the east side of I-15 that's flat black. I bet that thing gets so dang hot in there because it's just a heat sink, and that building envelope absorbs virtually 95 to 100% of all the heat that's in the sun rays all the time. That's heat gain. And then, of course, we have the gain that we produce by living inside that building. So we look at all these things, and then the last thing we look at, if I go back to that metal wire that I'm trying to cook a hot dog on, why does the heat move so fast? Two things. It's a conductor, and the second thing is I have lots of temperature difference. The temperature in my hand might be in the 80s, right? The temperature at the other end where it's in the fire might be in 600. And because I have that great temperature difference, the heat's going to flow quicker. So the heat flow by conduction is dependent on two things. How conductive or how insulated the material is and the temperature difference. If it's 40 degrees outside, does your furnace run as much as it does when it's 0? No, because the temperature difference or the delta T is greater. And so that's what we look at. And that's the design condition I'm talking about. What is the outside condition that we're designing for and the inside condition we're designing for. I don't need to spend more time on this. You can see that this is a little more extensive. I'm just going to mention real quick, ducts in attics. I've already talked about it. That's the number one thing we need to do something about. I got a phone call from St. George a week or so ago. They cannot get insulated flex. There's a material shortage, right? Can't get it. Guess what my first response was? Get it out of the attic.
Or condition.
Condition the attic or get it out of the attic. Get it out of the attic, you solve your problem. We don't have a heat loss and heat gain. They want to know if there's some way that they can do a little less insulation. Hell no. We don't want less insulation. Let's think real quick about it. I just mentioned insulation stops the flow of heat. What's the smallest R value that we see in the code? Ducts, right? What's an attic? 38, 49, 60, right? A wall. I just complained about R11 and R13 passing in a wall. But what do? We put a duct in an attic that has our greatest temperature difference that we see anywhere in a whole house in the summertime. Do you think they have 150-degree attics down here in the summertime? Absolutely. And you put a duct in it, and then you even do worse by suspending it above the insulation rather than burying it in the attic insulation. And then you blow 50-degree air through the inside of that duct with an air conditioner. We have 100 degrees temperature difference between the inside of the duct and the hot attic, and we are only stopping the heat with R8. There's something wrong with this, isn't there? Something serious wrong. Ducts and air handlers do not belong in attics. They literally do waste more energy than all the other stuff that we talked about.
It's even worse than that, especially in this part of the world, because in desert environments, because they put so much duct work in there, and it's so large that it displaces the insulation.
Yep.
So you end up with, you blow in the insulation, that 2/3 of the space is ductwork. That's R5, and so you got one big old hole in your inlet.
We got to take a break. We're not going to spend any more time on, but I'm just going to say one thing real quick. Look at the 18 and the 21 IRC, and look at what they're doing with ducts in attics and stuff like that, and trying to create insulation so they're outside the attic. Last comment is, if you're putting ducts in an attic, bury it into insulation and add some more insulation. So